Keith Grange.
Thanks very much. Hello, good afternoon. This afternoon I'm going to be telling you all about the Square Kilometre Array, or SKA, which is really going to be the future of radio astronomy. So without any further ado, I'll tell you a little bit about what the SKA is for in terms of the science that we're hoping to do with this new machine, and then exactly how we're going to achieve that, what the main structural components are going to be for this wonderful new telescope. I'll then move on to tell you about the work that I've been leading in the design for the telescope to do with the data transport and then also the time and frequency distribution. Because the SKA, I think it's fair to say, is a really, really big, with capital B, big data problem. And then I'll just sum up. So just to set the context for all of this, start with a quick history of the universe. The universe, we believe, is about 13.8 billion years old now. And the universe was born in a very, very hot Big Bang. Incredibly dense, incredibly hot, expanded very, very rapidly until after about 300,000 years, the universe had managed to cool to the point where you could form atoms for the very first time. There was then what's called the dark ages of the universe, where it's really rather hard to say what actually happened until the very, very first stars were born about 100 million years after the Big Bang. After that point, stars continued to be born and then form galaxies. Our own solar system was born maybe about 5 billion years ago, and then humans appeared very, very recently, only a couple of million years ago in the grand scheme of things. So that's the context of where we believe we reside today in amongst the whole of the universe. And for the last hundreds of years, the way that we've been studying the universe is through primarily the visible part of the electromagnetic spectrum. However, as this plot here is designed to show, that's only a very small chunk of the entirety of the electromagnetic spectrum, which goes all the way from gamma rays and X-rays over to the infrared, microwave, and then at the longest wavelengths, the radio. All of these are electromagnetic waves, waves that travel at the speed of light, but have very, very different frequencies. So very, very high frequencies, very short wavelengths on the left, and then in the radio, very low frequencies, very long wavelengths. And the thing is that actually in all of these wave bands, you can study the universe, and generally speaking, you see very, very different things. And so many of the advances in the last few decades have actually been made outside the optical band. The optical band is still very, very important, but actually exploring all of the electromagnetic spectrum is really the way forward. And actually, as I'll tell you in a second, there's really rather a lot of outstanding mysteries in the universe. And so what we're going to need is a new generation of observatories to tackle those. So here's the observatories that are coming online or already online that will allow us to do the next kind of push towards understanding our universe better. There's the EELT. This is a 30-meter class type telescope working in the optical and the infrared. We have superb sensitivity, allow us to do wonderful work. The ALMA telescope already exists in Chile on the Atacama Desert. That observes in the sub-millimeter. It's telling us a huge amount about star formation in our galaxy. The James Webb Space Telescope will be the successor to the Hubble Space Telescope, which has already told us a huge amount. James Webb will have more sensitivity and more angular resolution. And then the telescope that I'm going to spend the rest of today talking to you about, or the rest of the 45 minutes, don't worry, is going to be the SKA working in the radio wave band. So a potted summary of the SKA is that it's a very large radio telescope for delivering really transformational science, and has a total collecting area of 1,000 square meters, hence the square kilometre in the array in the name. It'll actually have baselines up to about 3,000 kilometers, and it'll work as an interferometer. And I'll come back to that and explain what that really means. It's working, as I said, in the radio wave band, all the way from 50 megahertz up to 15 gigahertz. So that's several meters kind of wavelength to centimeter type wavelengths. And because of that huge frequency range, it's actually going to be made as two separate telescopes using two very different technologies. First of all, aperture arrays at the low frequency end, and they're rather more traditional dishes, very much like the dishes that you can see out here in Jodrell Bank. As I mentioned before, the SKA is going to be a really, really big data project. It's going to have a phenomenal size, high-performance computer to actually deal with all the data it accepts, and then a very high-power optical network to actually move that data around. It's actually going to be built in two phases, but even this first phase, which is what I'm going to be concentrating on, is going to be 100 times faster than the best radio telescopes in the world today. So really extremely exciting. And the range of science that we hope to do with it is huge. It encompasses all of the topics down there. And we had a meeting a few years back in Sicily to think about all of the different science goals that this radio telescope would be able to tackle. That came in at 135 chapters, contributed by 1,200 different astronomers, captured in this giant tome of book here. It's 10 kilograms of book there, which encompasses just the projects that people are thinking about now. And if experience is anything to go by the time the telescope's actually up and running, we'll have thought of a huge amount of other projects to do with it as well. So I'll touch on some of the key science goals, the first one of which is to look at pulsars. Now, pulsars are produced by neutron stars. They're the leftover remnants from when a star dies. It becomes very, very compact and gives off bursts of radio emission. And there's perhaps tens of thousands of these pulsars within our Milky Way galaxy, which is what you're seeing here. And so with the SKA, we aspire to actually go and detect all of these, which is going to be exciting in its own right, but then we're actually going to be able to make use of the fact that these are extremely accurate clocks, as good or better than the best atomic clocks that we have on the Earth today. And so with these things, we're going to be able to do very precise tests of Einstein's general relativity and also look for gravity waves passing through the Milky Way. So we're going to actually turn the entirety of the Milky Way into a detector for gravity waves, which I always find is a rather mind-boggling idea. Secondly, we're going to be able to look for the very first stars in the universe. So what this animation shows here is a cube of the very early universe, about 100 million years old, filled with hydrogen. And the very first stars you can see being born, and those are now actually kind of blowing bubbles as they turn on by ionizing the hydrogen around them. So what's happening is these stars emit light and rip hydrogen atoms apart into an electron and a proton. And what you're seeing is the universe evolve, and as more and more stars are born, all of these hydrogen atoms being torn apart into just a plasma. And so one of the only ways that we're going to be able to actually study these very, very first stars is by looking at a unique probe called the 1.4 gigahertz hydrogen line. It's a way of actually studying this neutral hydrogen directly in the radio wave band. And so with this, we're going to be able to look at the very, very, very first objects in the universe being born. Incredibly exciting stuff. We're also going to be able to do some very nice tests of cosmology, i.e. how the overall universe on the largest possible scales works. So we're going to be able to explore some of our maybe largest unsolved mysteries through cosmology experiments. So first of all, we're going to be able to tackle the thorny issue of what's called dark matter and dark energy. Now, it turns out that normal matter, anything that you'll find on a periodic table from your chemistry lessons, is only about 5% of the universe. Then there's about 27% of the universe, which is some mysterious dark matter that we know must exist, but although we have some good candidates for what it might be, we don't really know what it is. And then the bulk of the universe, almost 70% of the universe, is this thing called dark energy, which I think it would be fair to say we don't really understand at all. So there's really quite a lot of work still to be done in cosmology because we only understand about 5% of the universe. And the way that we're going to tackle this is by looking at what's called weak gravitational lensing. So what we've got in this plot here is some background elliptical galaxies. And as the light from them travels towards us, they pass past some mass. And that mass actually bends the light exactly the same way as a lens would do. And we can detect that with a radio telescope like the SKA and start to deduce how much mass there is and how it's starting to clump and how it's been formed and start to work out what that tells us about the dark matter and the dark energy in the universe. Something which is a very recent discovery is called fast radio bursts. This is a plot of that you can just about see here. This stripe going across the plot on the right is some object having gone bang in a big way in the very, very distant universe, and we're seeing the light from it arriving at a radio telescope, actually one in Australia for this particular one. And this object emitted a huge luminosity of light, so a huge amount of energy in less than a millisecond or so. So something hugely explosive going off, and we don't really know what these objects are. So there's a lot of work to actually understand these things. Once we've actually found a few of them, we can actually use them to study the intervening universe between us and them as well. Another thing that is unique to radio is to be able to use what's called the Faraday effect and look at the polarization of light. So all light has a kind of handedness to it. You know this from if you've got polarized glasses, that if you put your polarides crossed with each other, no light gets through. Whereas if you have them oriented, light of that particular polarization can travel through the two. With the radio, that polarization, if it encounters magnetic fields, its polarization is actually bent. And so with observations of this polarization angle, we're actually able to deduce what magnetic fields are in the universe. And this turns out to be incredibly important because magnetic fields are vital for galaxy formation and also for the formation of groups of galaxies together, what are called clusters of galaxies. Final science topic that I'm going to tell you about is what's called the cradle of life. With the SKA, we'd be able to study new stars and new solar systems forming for the first time and actually look at the disks which will actually then coalesce and form planets. And we'll be able to also look for Jupiter-like planets, so really massive things giving off radio waves of their own. Very excitingly, we believe that there's actually quite a lot of complex organic molecules, so precursors for life, actually out in interstellar space, and we'll be able to search those from the emission lines that they give in the radio wave band. And then finally, there's the possibility that with the extreme sensitivity of the SKA, if you imagine that an alien civilization might use something like airport radar, exactly like us, the sensitivity of the SKA will be sufficient that we'll be able to pick that up from planets in a decent radius around us, about tens of light years or so. So we'll be able to pick up their airport landing radar with our telescopes. So SETI, that you'll have heard of before, is looking for alien civilizations which have beamed messages towards us. This experiment will pick up intelligent life if it's out there and if it's using anything like our radar systems. Right, so hopefully that's convinced you that we're going to be doing something really exciting with this telescope. How are we going to do it? We're going to use a technique called radio interferometry. This technique is used for some of the telescopes that you see just outside this tent. For example, the E. Merlin telescope. The idea is that you use several separate radio telescopes and then combine together the signals from those. And by doing that, you can actually make a telescope whose angular resolution is as good as the distance between the most distant of those telescopes. So, for example, the E. Merlin telescope has an angular resolution as good as a 220-kilometer sized telescope, which, of course, would be really rather difficult to build on its own. However, I mean, that's great. However, the sensitivity of the telescope depends upon the collecting area. And to actually tackle all those really exciting kind of science goals that I was just outlining to you, you really need about a square kilometer of collecting area. Hence, our drive for actually building the SKA. So, what are we actually planning on building? Well, we're going to be going to two sites, one in South Africa, one in Australia. In South Africa, in the Karoo Desert, we're going to be building almost 200 dishes. So dishes very much like the ones you can see out there, each of them 15 meters in diameter. In Australia, we're going to be building a much simpler type of antenna, something which you can see looks very much like a glorified television aerial. However, we're going to have 131,000 of these things. Okay? The reason that we're putting these telescopes in those two locations is to get away from people, basically, and in particular from the radio frequency interference from things like microwave ovens, mobile phones, arc welders, whatever. And so we want to go to a very, very quiet site. So here's the picture of the Karoo Desert with an outline of how you would go and deploy the SKA antennas. And you can see that we're well away from the most inhabited bits of South Africa. Really critical to be able to make the very, very sensitive observations that I was talking about to tackle those science goals. One other thing just to note is the configuration of these antennas that we're going to have is going to be a central core of a large number of these antennas and then spiral arms going out. That gives you the best imaging for an interferometric radio telescope. And as I say, these telescopes are going to be 15-meter in diameter, and we're going to have them scattered up to 150 kilometers apart. In Australia, we're going to have be basing the telescope there in the Murchison, and this really is remote. This area that I've got put on the map here is the size of the Netherlands, and it has a total human population of 110. So we're well away from a lot of contamination. There's plenty more sheep and cattle, of course, but we don't have to worry about those quite so much. And there we are going to be using, here's a bit of a better picture of these log periodic antennas, these things which are fairly much glorified television antennas. And what we're going to do is going to produce groupings of 256 of these things, which we call a station. And then we have 512 of those stations scattered over the Australian desert with up to 65 kilometers between the most distant ones. So the SKA project itself is a very much global project. We've got now, I think it's 11 or so different member countries, and the hope is that in the future, when we move to phase 2, we'll have a whole bunch of other African countries where we will have groups of antennas going all the way up through Africa to provide these 3,000 kilometer type baselines that I was talking about. And this international project is actually headed from a headquarters, which is 100 yards or so over that way. So in, yeah, it's great for, yeah. And this was actually opened just a week and a half ago. So really exciting time for us. The design work for the telescope is really quite well advanced. The design work's been conducted by 9 international consortia, with the UK leading 2 of those. The one which I'll talk most about, the signal and data transport, but also the science data processor, the really high-performance computer part of the telescope. And the UK has committed £100 million towards this build, and really has actually kind of brought the entirety of our international community along, I would say, to making sure that this thing is really realized. And I'm very glad to say that, again, it's a rather exciting time, because the SKA is going to be governed by an intergovernmental organization, and the treaty to set this thing up was actually signed in Rome just a few months ago. So this is really going to happen now. And previously, when I've given such talks, I've been saying, oh, well, in the future, we'll set this up. People, real serious governments are now coming along, putting their signatures to the treaty to set this thing up. Really exciting times. So, I've said that the SKA is a big data project. I just want to now tell you a little bit more about that and how we're going to tackle it. And also just to try and set this in some kind of context. A few years ago, when we started this project, the world's total internet traffic was about 80,000 gigabits per second, okay? So that's a number just to try and hold in your mind. The entire internet, a few years ago, 80,000 gigabits a second. So what do we have to deal with for the SKA? Well, we've got our 2 different types of telescopes producing 90 gigabits a second and 10 gigabits a second, but we've got really rather a lot of them. And so we have roughly about a third of an internet coming through the desert to a central building where we do lots of processing work in a correlator and a beamformer. We then take another 20% of an internet and take it about 900 kilometers out of the desert towards Perth and Cape Town. There's a supercomputer which produces lots of interesting science products, and we have about a petabyte per day of data being produced by this. We then have to take that reduced data and take only about 100 gigabits per second and distribute it all the way around the world to the world's astronomers. And that's the job that I and my team had to try and tackle from about 5 years ago. So now I'll tell you how we got on. So, in fact, that's only one of the things that we had to do, producing this network for the data transport of the astronomy data. We also had to work on what's called the synchronisation and timing. Now, the way that these telescopes work as an interferometer, I said you'd combine together the signals from lots of different antennas, which is fine, but it does mean that you need, at each antenna, a very, very accurate clock so that they're all in step with each other. And the kinds of accuracies that we're talking about are a millionth of a second. And so you've got to get an accurate clock to a millionth of a second to each of these antennas lying up to about 150 kilometers apart. So that was another challenge. And then producing a network which actually allows you to control the whole telescope and gives you security as well, so you don't have people hacking into the telescope and just driving it off to point at strange things. Each of these networks has its own individual set of challenges. And this all of these challenges were tackled by the Signal and Data Transport Consortium, which I led. The consortium was made up of 14 different institutions from 8 different countries. And it was great having this wealth of real expertise from true world-leading experts in their fields. As you can imagine, though, having people from China and Australia and South Africa and Europe all trying to work together made actually quite a difficulty in, if anything, just scheduling times where we could all meet up. So, how did we go about doing the design work? First of all, we had to get the data from these individual antennas back to this central building in the middle of the desert. And so we're using fairly much standard commercial, off-the-shelf equipment, but producing about 100 gigabits per second, but we've got 133 antennas, or 512 stations in the case of the low-frequency telescopes. And these things are scattered all over the desert. So the trick here is it's a moderately large data rate, but getting the data from all of these disparate antennas all to get to the same place is the trick. And we've now actually got a prototype of this running in a shed just over there, which demonstrates that we can actually do this. The other thing is that this will need a huge amount of optical fiber to actually have the data transported over to this central building. And here's some trucks showing you exactly what this kind of looks like for one of the prototype telescopes, for the ASCAP telescope. So a huge amount of optical fiber going into here, and you've got trenching as well. What always strikes me as slightly odd is that of all the things that I'm going to be telling you about the design of the signal and data transport, the digging holes and putting glass into it is by far and away the most expensive bit, which just seems wrong compared to all the really cunning, high-tech stuff which allows you to do a third of an internet's transport. The next challenge is to get this kind of 20% of an internet out of the desert. And here the challenge is, it's all going in the same direction, so that's good. But we've got a huge volume of data, this 7.8 terabits per second. And the thing that we're going to use here is, again, optical fiber. But it turns out that down a single pair of optical fibers, you can put lots of different laser lights, lots of different colored laser lights. So maybe up to about 100 or so. And so what's really quite incredible is that even that huge volume, it turns out that you can put all of that down just a single pair of optical fibers. And so actually in Australia, where we've got 24 pairs, we're going to use one, and we've got 23 spares. Along the way, we're actually going to have to multiply up the signal because the signal gets degraded as you travel more than about 100 kilometers or so. So we're going to have these self-sufficient amplifier huts, which are all powered by those solar power units that you can see here with a backup diesel generator at the back. And this, again, is a prototype of that system. Works very nicely. And then the final one of the data transport issues is we'll have the data conglomerating in South Africa and in Australia. How do we get that out to astronomers in Europe and Canada and India and China? We're going to be using very big submarine cables. Fortunately, those things already exist. We don't have to build them ourselves. And we're going to be piggybacking off the work from national research networks here. We also, at the same time, have to produce a network which allows us to control the telescope, gets all of these telescopes, as I said before, actually have to work together. They've got to be pointing in the same direction so that you can actually combine the signals together. So we need a network which allows us to do the telescope control, allows people to access the outside world, provides phones and things like that, and also deals with security. So we've designed a network with resilience, so if things fall down and break, then the whole telescope doesn't just grind to a halt. I mentioned before that the telescope has to work with a degree of synchronization. That means that the different antennas have effectively a common clock, even if they're scattered around the world. And so the accuracy that we need is this millionth of a second, a picosecond of timing accuracy. And what we're going to do is distribute a clock signal down fiber optic cables. And that's fine, except that, of course, as the temperature changes, these fiber optic cables stretch. And their length changes, which means that things become delayed, and all of a sudden your clock isn't accurate anymore. And so colleagues in Tsinghua University in China and University of Western Australia have come up with two very cunning schemes of actually using a signal to go out to the telescope and then back again to actually correct for that effect. That allows us to have only a central single clock made up of hydrogen masers, as shown in this diagram down at the bottom. These are incredibly accurate clocks. We've put 3 of them together to give a certain amount of redundancy, and then distribute out that clock signal. And what we want to aspire to is, in order to do those kind of pulsar experiments that I was telling you about, to measure gravity waves and also test generativity, is to get a clock which is accurate to 10 nanoseconds over a period of 10 years. So again, we've had to think about how do we calibrate that against the world's timescales in order to try and get to that level of precision. So I'm glad to say that all of this work we've actually successfully completed now. We did the design work and summarized it in a grand total of 279 documents, which we gave to the SKA organization, again, residing just over there. And they had a look, came back with just over 1,100 comments. We discussed these over a 4-day meeting, and then changed the design to suit, and have now passed this milestone of what's called a critical design review. And the design's been accepted, and we've handed over the entire design over to the SKAO, and they've incorporated that into their baseline. So that's great news for us. So, thank you very much. So the consortium's done its work. We've kind of wound down the consortium. There are some bits of what's called bridging work that we still need to do to help out with changes to the design, which are always happen in a project like this. People's ideas evolve, and we need to tweak things, but the bulk of our work is done. This is also the case for the majority of the other consortia. The vast majority of them have passed their critical design review. There's only one outstanding consortium, which is running a little bit late, and that's going to allow everybody to then do a design review of the entire telescope, which is scheduled for December this year. And then that will allow us to actually start building in 2021. There's a 7-year construction period, so it's going to be until 2028 until this thing's finished. But the exciting thing is that because this is a radio interferometer, and what the way it works is by taking signals from different antennas and combining them together, as soon as you've got more than 2 or maybe 3 telescopes, you can actually start turning the thing on and start doing some science. And so from about 2025, although it's only halfway through the construction period, it's already the most powerful radio telescope on the planet. So I'm already looking forward to doing early science with the thing. So just to finish off, I'll give you now some videos of artists' impressions of what the SKA will look like. So this is the telescope in South Africa, made up of these mid-frequency dishes, 15 meters in length. What we're doing is flying along one of these spiral arms and moving into this core of antennas in the center. And we have a huge number of these antennas in the center for doing things like the pulsar type experiments. And then moving over now to Australia, we see much the same thing, except that the desert is a slightly different color. And here you can see these stations, these collections of radio antennas moving into a core. And you can see that you almost have a sea of these antennas. These are the 130,000s worth of antennas that we have here. So, of course, those are artists' impressions. From 2021, we'll actually be building it and realizing the real thing. So, just to sum up, the SKA will actually be the largest scientific project on the Earth once it's actually up and running. We're actually going to need the help of industry to build this thing. It's just too big for the way that we traditionally do radio astronomy, of having universities and research institutes doing it. We need industry to get in and start building this stuff. There's actually going to be very major benefits, therefore, to the participating countries with industrial contracts flowing to them. And then we expect the SKA to actually have a lifetime of about 50 years. And it really will be powerful enough to deliver really transformational science. And indeed, I would say that in some of those key areas that I identified at the beginning of the very earliest stars in the universe, this cosmic dawn, and the detection of gravity waves and clues as to the origin of life, all of those have the potential for being so exciting discoveries that they may well win a Nobel Prize. So let's hope and look forward to that then. Thank you very much indeed.
Okay, thank you very much, Keith. We've got about 5 minutes or so for questions. If anyone has any questions, just stick your hand high in the air. There's just a mic behind you.
Hi. Recently, they actually made a picture of a black hole using many telescopes from around the world. Now, I'm guessing SKA will be able to do the same with very long waves, so you can piece together a very long wave coming from somewhere. And I would like to ask what kind of objects could give really, really long waves?
A very, very good question. That was one of the kind of science highlights that I wasn't able to go into. Just because there is so much exciting stuff to say. It is certainly one of the aspirations that people are already thinking about of designing into the SKA, is to allow the SKA to actually work as just one more station combined with other radio telescopes around the world to give you extremely long baselines and give wonderfully high angular resolution, a technique called very long baseline interferometry. So that's already definitely in the works, in the plans, and should deliver some extremely exciting science as well. Yeah, good question.
Why do you have two different types of telescopes as opposed to just one in both places?
Very good question. In an ideal world, yes, we would actually just reuse the same telescope for both sets of observations. The trouble comes because the range of frequencies, or maybe better to say, the range of wavelengths that we're looking at is so long. So down at the longest wavelength, the wavelength of the light is 6 meters. And a 15-meter telescope is actually very, very poor at concentrating those radio waves. And so for that kind of observation, we've had to move towards stations made up of these individual antennas, which you then electronically phase up together. You can't then, unfortunately, use those same antennas to look at 2-centimeter wavelengths, so the 15 gigahertz, the high frequency end of the thing, because the distance between the individual antennas becomes so large compared to 2 centimeters that the things actually have very little sensitivity at all. So in an ideal world, I would completely agree. We'd just build the one telescope. Practicalities actually mean that we can't. Nice question.
Hey, continuing on from that question, I guess, with if you've got 2 different types of antenna and you're carrying it across 2 continents, how do you, from an engineering perspective, how do you keep time across the 2 continents if you've got to go all that way around the world? You've got a local version of time through the nuclear, the laser hydrogen timing. How do you keep it across the entire world?
Right, okay. So we're not actually going to try and combine the signals from the 2 separate telescopes with each other, but we are, as I said before, going to try and combine the signals from those telescopes with other telescopes. So your question is still very much on point. What we're going to do is actually those hydrogen masers. What we need to do is actually take the signals from those, the individual clock produced from those, and transmit it via satellite back down to the BIPM in Paris. There they actually managed to concentrate all of the atomic clocks around the world and actually come up with an average kind of time, and then you can, in processing, actually correct for any errors in the time between your clock sitting in South Africa and the clock or the clock made up from the average of all the world's clocks in Paris. So it's done in post-processing with a very complicated calibration scheme.
Yeah. What will there be a role for Merlin in a post-SKA world?
So, simple answer, yes. And I'll try and explain more why. So Merlin is, it's got longest baselines of 220 kilometers and is working in the same kind of frequency range. It has nowhere near the sensitivity of the SKA. However, and this is going to now sound a little bit parochial for the UK, but what astronomers are going to be able to do in the UK is say, oh, I'd like to study this. I'm going to get some time on Merlin, study a couple of these objects, and then say, oh, my project really does work. I've demonstrated it. I would now like to run this for several hundred objects on the SKA. And the powers that be, the time allocation committee, will hopefully look on that much more favorably because you've really demonstrated that the thing can work with eMerlin. So the eMerlin certainly does have a very significant role going forward.
You've got on the screen there that it's going to be delivering projects for the next 50 years. What happens after that time?
Shall I rephrase it to at least 50 years? Because, I mean, for example, the Lovell Telescope out there was built in 1957. Still doing world-class science now. In fact, it turns out that as long as you've actually got the metal on the ground, you've got the dishes, you've got the antennas, as technology progresses, you can come along and update the back-end receivers and start giving a new lease of life to older telescopes. And that's exactly what's been done with the Lovell Telescope. There's been several iterations of upgrades which give it, keeps it at the cutting edge of the world. So I think technically we've said that after 50 years we have to have a plan for decommissioning the telescope. But I would certainly think that it's quite likely that that infrastructure that we've built up will continue to be useful even after that, after you've had a major upgrade. Nice question.
Okay, unfortunately, that's all we've got time for. If anyone's got any more questions, please visit the SKA stall down in the Starfield. Otherwise, let's give another round of applause to Keith Grange.
Thank you very much indeed.